I'll be looking at the chat. I just started recording so people can see it. All right, so I'll start by going through what we went through really quickly at the end of last class, which is conditional probability, right? So the way that you write conditional probability, as I went over, is that if you're trying to find the probability that event A happens given that event B has happened, you write it like this. And the definition gives you this formula. So probability of A intersection B divided by the probability of B overall. So if A always happens when B happens, then the A intersection B will be exactly probability of B, and this will equal to 1. Okay? And I also went through Bayes' theorem, which you can kind of derive through, if this is A given B, and this has the A intersection of B, then if you find the probability of B given A, it would also be the probability of A intersection B. This does not change. The thing that changes is the probability of A is underneath now. So if you take both of these terms, you notice that they're equal, right? And so if you rearrange this here and you rearrange this here, what you get is probability of A given B multiplied by the probability of B equals to the probability of B given A multiplied by the probability of A. This is just one formulation of Bayes' theorem. And sometimes you'll see that it's like A given B equals the probability of B given A times the probability of A divided by this, but it's just like you reconfigure it. So it's not really anything different. This isn't only useful in statistics, it's also useful in your micro class. Towards the end of your micro class, you'll start using probabilities in order to find out useful outcomes. So yeah, in the future, this will also be used quite a bit. And then I didn't go through independence, but now I want to go through independence. So two events are known as independent if one event having occurred does not affect the probability of the other event occurring. So if the probability of B, given that A has happened, is still the probability of B, then we say that these two events are independent. And I think from there, you can kind of intuitively understand the idea of independence as like the event A has no effect on event B. Because if event A happening had an event on the had an effect on the probability of event B, then this would have changed, right? But let's say I'm like, I trip and fall today, and this has no effect on whether or not I will win the lottery tomorrow. Those two events are independent because there's no change. Like if I trip and fall today, it's not more likely that I would win the lottery tomorrow, and it's not less likely that I would win the lottery tomorrow, and vice versa. So then you can say those two events are independent. A lot of people confuse independence for being mutually exclusive. But also something I wanted to discuss really quickly is that a lot of people have probably seen you take the probability of A intersection B equals to the probability of A times the probability of B. This means that it's independent. But where does this formula come from? Well, from just now, going by Bayes' theorem, probability of A, no, not going by Bayes' theorem, going by the definition of conditional probability. This probability of A given B is A intersection B over probability of B, right? So then I multiply this over, and I have the probability of A given B multiplied by the probability of B equals to the probability of A intersection B. But then, if A and B are independent, we will see that the probability of A given B is probability of A, like if you swap these two around. So if the probability of A given B is just probability, this is just probability of A. Then you get the identity where you take the probability of A multiplied by the probability of B, then you get the intersection, probability of A intersection B. And that's how you basically show independence. And yeah, is everything clear so far? Oh, someone had a question. Oh, sorry. Yeah, I'll slow down. But yeah, basically, yeah, so I'll just talk, I guess. Sometimes people confuse independence with being mutually exclusive. And it's actually a really common point of contention where people would like confuse the two. But independence and mutually exclusive is kind of like quite opposite. Because if event A happens means that event B won't happen, that means that event A having happened had an effect on event B, right? Like if I say that once event A happens, event B will never happen. Unless event B will never happen in the first place, that means that once you know that event A has happened, then you know some more information about event B. So yeah, like mutual exclusivity, I think it'd be better for me to write that down in formal terms. Okay. So if, let's say, mutually exclusive is defined as the probability of A intersection B equals to 0. But if the probability of A intersection B equals to 0, that means that if they are independent, it must be that probability of A multiplied by the probability of B equals to 0. So it is, by definition, unless an event never happens, it cannot be mutually exclusive if it is independent. Does that clarify that? I hope it does. That I feel like that explanation was a little bit confusing. But if you want me to explain it again, yeah, it was good? Okay, awesome. Now, I guess we'll move on to some probability exercises. And I feel like the most important thing is that I walk through the wording of the question. So if you could, let me just send the tutorial material to the chat in case y'all didn't see it in the, okay, let's see. Yep. Sorry, just need some time to get to that directory. All right, it's this one. Okay, so I sent it in the chat. It'd be very, very, very helpful for you to open up the PDF and follow along, because the whole point of this is that you read the wording and you understand the wording, and then I'll explain to you the wording. So the first question is that government economists have constructed an indicator that has 3 states, red, amber, or green, of the stress on the financial system, which they intend as a signal of risk that the economy might enter into recession. So the indicator is found to perform as follows. When you see that, when you start seeing numbers, that's when you should start writing it out in mathematical notation. Okay, so first I want to define a few things. And the first thing that you should probably do is define a few things after you read the question. You see that I'm going to define red, R, as the event that indicator is red. Okay. A is the event that the indicator is amber. G is the event that the indicator is green. And since you care about whether or not you're in recession, so recession or not recession, you also have to define, I'm going to call it N because recession is a negative growth. So it's the event that economy goes into recession. Okay, and then now you look at the thing. What does it say? When the economy does enter recession, so you're given that the economy enters recession, right? So probability, you're given that the economy enters recession, then you add this already. Like then you're waiting for this thing to be added. Like you're waiting for the event. So the previous month's indicator was red 60% of the time. So you would put red equals to 0.6. Amber 35% of the time. So what you would do is put amber 35% of the time. Right? And finally, green 50% of the time. Wait. No, green 5% of the time, sorry. Probability G given N equals to green 5% of the time, so it's 0.05. And if this all like checks out, then all of this should add up to 1. Because if you're taking the given, there's only 3 states that the indicator could be before. So all of this must add up to 1, because if you know that a recession has happened, there must have been an indicator in the previous month. So it must all add up to 1. So this is basically how you interpret the question. You must be very careful that, because if you just see like the previous month's indicator was red 60% of the time, then you might think that, oh, okay, the probability of the indicator being red is 0.6, right? But that's where the wording is very, very tricky. So for each line, especially when you start writing down numbers, you have to be very careful that each of the numbers that you write down are correct. Not only that, because once you start off with a wrong number, you'll just go in circles and circles and circles, and you'll never be able to get the right answer. And because all of this wording is very ambiguous, the best thing you can do is immediately define all the events, write down the probabilities, and then for the question, you write down which probability are they trying to make you get. And then when you see everything in symbols, it's much easier to understand. Then you try to figure out what his wording is. Okay, and then whereas overall, the indicator is red 0.2% of the time, right? Like, so 20% of the time, right? So overall, which means no condition at all, the indicator is red 20% of the time. No condition at all, the indicator is amber 30% of the time. So we put 0.3. And overall, the indicator is green with 50% of the time. Does this make sense? All right. I need some space, so I'm going to erase this, but I think these make sense, right? So red is R, A is amber, G is green, N is recession. So, oh, finally, over long spans of time, the economy is in recession 10% of the time. So we also have Pn equals to 0.1, but I'm going to separate it from this. Because the probability of all the indicators being a certain, like, all of these must add up to 1. Because the indicator is either red, amber, or green. It can't be nothing. So all of these, you have to remember it must add up to 1. If it doesn't add up to 1, and you know that those are the only 3 possibilities, then something is wrong. All right. So the first question, find the probabilities that the economy will enter recession next month if the indicator is red, amber, or green respectively. So what is this question trying to ask you? Is the probability that N happens given that R, that's the first thing they're asking. Next thing, probability that N happens given A. And the final thing, probability that N happens given G. Now, if you don't write this question down in symbols and you're just trying to think, oh, how would I know what are the probabilities that the economy will enter recession next month? Kind of seems like it's being plucked out of nowhere, right? But once you write it down into these symbols, and you know that you know all of this information and all of these information, then the problem becomes much more simple, because this is just a Bayes theorem problem, right? By the definition of this, you know that this is the probability of N intersection R. Actually, we should just apply Bayes theorem directly. So this is the probability of R given N multiplied by the probability of N divided by the probability of R. This is exactly Bayes' theorem. And once you write it down in all the Bayes' theorem form, even if this doesn't really even make sense to you as an expression anymore, you just look for something with the same symbols. Does this have the same symbol? It does? Okay, this is the number from here. Does this have the same symbol? Okay, this goes here. Does this have the same symbol? This goes here. And now you computationally know that the answer is 0.6 times 0.1 divided by 0.2. Does that make sense? And then like the final answer is 0.3, but that's not really the important part. The important part is that the most important part is that you look at the question, you turn and look at the question and all the information that it gives you, you can turn it into symbols. And you can move from this symbol to other symbols that you know the answer of. So you see this, your first thought is, oh, conditional probability, right? So Bayes' theorem, you write it like this. You think, do I know all the aspects of this equation? Do I need to turn, if I didn't know this, maybe I need to turn it into something else, right? Like if I didn't know this, I didn't know both of this, but I knew the probability of n intersect R, then I wouldn't use Bayes' theorem. I would just use the definition of a conditional probability. So the whole of statistics, yes, sorry.
No, I was just wondering how you got that equation on the top.
Oh, this one. So this is Bayes' theorem. So Bayes' theorem, I'll show you how to derive it now. Actually, I think now that you understand, I'll just clear space here. I don't want to erase the equation itself so you can see exactly where I'm going with it. So the probability of n given R by definition equals to the probability of n intersection R divided by the probability of, the probability of R. Does this make sense? Okay. But then what we also have is the probability of R given n equals to the probability of n intersection R divided by the probability of n. This is the exact same thing. You just change R and n, right? So the intersection of n with R remains the same, which means you can equate these two things, right? So let's say I move this over, I move this over, and then what I end up with is probability of R given n multiplied by the probability of n equals to the probability of n intersect R. Okay? And then this is n intersect R, right? But this is also n intersect R. So if you move this all the way over here, then you get exactly this. And that's how you derive Bayes' theorem. Does that make sense? Okay. So then once you have this one, you see that I don't know n given R, but I know R given n. That's the number one signal for you to start using Bayes' theorem. That's like the instant, like, oh, okay, I know R given n. That's the first thing I'm going to try. Because not only do I know R given n, but I know the probability of n, and I know the probability of R. So you already know all of the essential components to this equation. And since you know all of the essential components to this equation, you can solve this. Does that make sense? All right. So I'll erase this part. I'll keep the important numbers. So these are all the important numbers. And then we'll move. Oops, I erased one of the important numbers. Give me a second. Okay. And then we'll move on to the second part, which is the probability of n given A. This is the second part of the question, right? what is the probability that the economy will enter recession next month if the indicator is amber? Well, you saw the trick just now, right? All you needed to know is the probability of R given N to get the probability of N given R. So now you have the probability of N given A. The first thing you should do is look, okay, I have the probability of A given N. That's great. Do I have the probability of A? Yes, I do. Do I have the probability of N? I also do have that. So it's the exact same thing all over again. You write the probability of this as the probability of A given N. This is given, by the way. Multiplied by the probability of N divided by the probability of A. And then if you look at everything you know, you have A given N. You have N. And you have A. So with a bit of computational magic, it'll just be 0.35 times 0.1 divided by 0.3. But this is the least important part. The most important part is that you got from here to here. And the step where you know every single part and you know how to plug in all the numbers already, everything beyond that is just trivial. You find a number, you put it in. You just need to get to the point where you're like, oh, I know all of these variables, right? If I just use the definition of conditional probability here, okay? And instead of using what I had before, I had this. This does equal to this, like the probability of N given A does equal to the probability of A intersection N divided by the probability of A. That's true, but it's not useful. Why is it not useful? Because I don't know what this is, right? The most important thing is that I move to a point where I know what everything is. So even though this is correct, like technically correct, doesn't get you any closer to where you want to go. So yeah, most important thing is you know how to interpret the question and move to where you want to go. And then the last part is the probability of N given G, which honestly, you just do the exact same trick as before, right? You just do probability of G given N, multiply the probability of N divided by the probability of G. G given N, we have it. Probability of N, we have it. Probability of G, we have it. So we have everything we need. Everything else you can just calculate yourself. That's the part that doesn't matter. So I hope that got you more familiar with moving around conditional probabilities. And now we'll be adding something that is the complement. The next thing that they want you to do is find the probability that the economy will not enter recession next month if the indicator is red and if the indicator is amber. Okay, so the probability that the economy will not, remember this sign, this overline means that this event does not happen. The opposite, the complement of a recession happening is a recession not happening, because there is nothing in between. You can't have a half recession, right? So if a recession does not happen, you are not in a recession. So you're asking for the probability that the economy does not enter a recession next month if the indicator is red. The other part is the probability that the economy does not enter the recession next month if the probability is, if the indicator is amber, right? And then you use this really useful trick, okay? This is just simply 1 minus the probability that that you experience a recession next month, given that the indicator is red. Why is this true? It's because given the indicator being red, there are only two possible states after that. You can either go into recession next month, or you can not go into recession next month. So you either this happens or this happens, which means that this plus this equals to 1. If the indicator is red now, it will either go into recession next month or it will not go to recession next month. This will definitely happen. Does that make sense? So since you either have one of these two states, so then the probability that you have a recession next month, given that the indicator is red, the probability that you don't have a recession next month, given that the indicator is red, it's basically saying what's the probability, so it's basically saying that this one or the other will definitely happen. Another way of saying that is the probabilities add up to 1. Because these two can't happen at the same time. This would not be true if these two could happen at the same time. But as we mentioned, a recession can't happen and not happen at the same time. So that's why you can add these up to 1. Because n and n complement are mutually exclusive. They will never happen together. But one or the other will always happen. Not only is it mutually exclusive, but it's exhaustive. Do you have any questions about that? I can see how that would be kind of confusing. Yeah, so if you have no questions about this, this is the most useful trick that you will see because it saves you a lot of computation. One thing that you'll notice about stats is that there are many different ways to solve problems that could get you the right answer. So another way I could have done this, instead of doing this really fast trick, let me just try it now. Maybe I could have done it like n r equals to the probability of n intersection r, which is over the probability of r, which is the probability of n intersection an intersection r. Summary is that it's just really long and you really don't want to do it like that. So yeah, like there are many different ways to get to answers that you want. But you will soon find that some answers, like some ways are better than others because they require less work. Why does this require less work? Because you already know what the probability of n given r is, because you derived it just now. Just now is 0.3, right? So 1 minus 0.3, which equals to 0.7. So yeah, I mean, like you could technically go through all the hoops and re-derive it. But why would you want to do something like that when you can just as easily do this? Same deal with the probability that a recession does not happen given that the indicator is amber. This is also the 1 minus the probability that a recession does happen given that the indicator is amber. Because one or the other must happen, but they cannot happen at the same time. If one or the other must happen, then they add up to 1. If they cannot happen at the same time, then you know that it's only these two cases. There's no intersection. Like, because there's no case where like, oh, you have to take the intersection of A given, and you minus this away. This is equals to 0. So you don't have to minus away anything. All right. Any questions about that? Okay, if not, I suppose we can move on to the next question. I don't like how Galbraith solved the next question because it's the same thing that I mentioned to you. Some methods just require more work. If you look at the answer sheet for this question, the way he did it was very, very long and tedious. You can do it in 2 steps. Okay, so consider events C and D. The probability of C equals to 0.2. The probability of D equals to 0.3. You have that C and D are independent. So find the probability that C and D will not both happen. Here is where we use our wonderful Venn diagram, okay? He gave a nice helpful clarification. The probability that one of them may happen or neither, but not both. So the only condition is that both of them does not happen at the same time. C can happen, D can happen, but C and D at the same time cannot happen. So looking at this, where is that in this wonderful Venn diagram? Well, this intersection cannot happen. So what we're looking for is everything else. Okay, everything else. We're just excluding this intersection, right? Another way to write that is you write the probability of C intersection D. We take this, right? But then we want to take everything other than C intersection D. So you just draw a big overline over it. Does that make sense? Okay. So neat trick. Since C and D are independent, the probability of C intersection D equals to 0.2 times 0.3. Wait, no, sorry, I should have put that in symbols. The probability of C and D both happen is the probability of C multiplied by the probability of D. This is only under the situation where they are both independent, as we have mentioned before, but they are, which is perfect. So then we know that it's 0.2 times 0.3, which means that it's 0.06. Okay? Now, you want to find everything else. So if you want to find everything else, everything that is not this, it's just 1 minus the probability that this happens, right? Because if the probability that you're within this space is 0.06, and the probability of the entire space is 1, if you want to get to every other point, you just do 1 minus the probability that you're in the space that you don't want, which is 0.94. Okay? And this is a really simple solution to this problem. Sorry, Paul has a question.
Oh, yeah, I was wondering if you do the complements, if we say that it's a complement of C intersection D, can we write like another formula, which is then P complement C times P complement D, or does that not work?
P complement C. No, it doesn't work.
No, it doesn't work.
Because the complement belongs to both of those intersections. So
I see.
Okay, so I can draw you the Venn diagram, okay? P complements C, like complements, okay. What you said was the intersection D, right? I'll show you why this doesn't work. The complement of C is everything outside this circle. The complement of D is everything outside this circle. What is their intersection? It's everything outside the two circles, right? But then you notice that this picture is different from this picture. You're supposed to exclude these parts. But if you take the complement of C and you intersect with the complement of D, you don't exclude these parts.
I
I
see.
feel like what you're thinking of is another well-known identity. And what that is, I'm sure you know De Morgan's law, right? Which I covered last time. But if you don't, De Morgan's law says that this equals to the probability of C complement union the D complement. This is correct. This is correct. Okay.
I see.
And then this,
Okay.
because what you do, you take C complement, everything outside of this circle, union D complement, everything outside of this circle. So this is effectively saying you just take everything outside of the inner circle. If I draw the Venn diagram for you, it doesn't make much sense. But if you really want to convince yourself of this, draw the Venn diagram yourself. And you will be very convinced. Once you do it once and you'll be like, oh, okay, I see it. It maps to exactly the same thing. But it is true that Galbraith used this method of solving this. So when you take the union, this equals to the probability of C complement plus the probability of D complement plus the probability of C complement intersection D complement, okay? And this is the probability, 1 minus the probability of C, 1 minus the probability of D. This is, you take this C complement intersection D complement equals to probability of C complement times the probability of D complement. That's what Galbraith's method was. And it's correct. Don't get me wrong, it's very correct. But it's also a lot of work. And why would you do so much work when you can do it in 2 steps? It's like, yeah, like there are some methods that work and you should go with whichever method it works the best for you. But if you want to learn a method, the best thing that you can do is learn the best or fastest method. It's useful to know how De Morgan's law works. That's true. But also, if you wanted to know how De Morgan's law works, you should find a question where you can only use De Morgan's law to solve it. You shouldn't use a question where you can use so many other methods that are better and faster to solve it. Does that make sense?
Yes, thank you so much.
All right. So I feel like I should probably skip to the combinatorics part. I'm always so ambitious. Okay. I'll just skip to the combinatorics part because the rest is honestly a lot more of the same. I left a few, like all the extra exercises that I have, you can just like look through the questions, work through it, and you can look at my answers, which is the same as Galbraith's answers. It's just typed out so you can read it better. Yeah, it doesn't really make a difference. So now we'll start with combinatorics. The first thing about combinatorics that I feel like you should learn is the factorial operator, okay? The factorial operator is such like this, n factorial. You call this n factorial. This equals to n times n minus 1 times n minus 2 ... times 1, okay? And it's like, why do you care about factorial? It doesn't really make much sense to you if you're just trying to do stuff, right? So I'll give you an example of why you should care about factorial. And the reason why factorial is important is because it's related to ordering. Let's say I have 3 balls in a bag, okay? 3 balls in a bag. I want to draw them out one by one. So let's call the balls B1, B2, B3. How many ways can I draw out 3 balls? One way that I can draw out 3 balls is B1, B2, B3. Sorry. Another way that I can draw out 3 balls is, let's say the first ball I drew was B2. The second ball I drew was B3. And the last ball I drew was B1. right? But if you want to write down this, it's doable when there's only 3 balls. But what if I told you there was 600 balls? How do you know how many ways there are to order 600 things, right? So a very useful life hack is that we use the factorial operator, okay? So I'm just gonna write 3 places. When you're drawing the first ball, you always have 3 options because you have 3 balls. This one can be B1 or B2 or B3, okay? Let's say we set this as BX. You set this already. This one, like, okay, never mind. I think BX makes it confusing. Let's say we happen to draw the first one as B1. But that means that B1 cannot be drawn again. So how many options do we have left here? Just now we had 3 options here, right? We happen to draw B1. Over here, we know that we cannot draw B1 ever again because it's already out of the bag. Oh, I should have used cats. Sorry. Yeah, the ball is out of the bag. So there's only B2 or B3 left. So there's only 2 options left. So there's 2. Let's say I happen to draw B3. For the last one, I only have 1 option left. There's nothing else. There's only 1 ball left in the bag. This has to be B2. So what you do is you multiply these 2 and you get 6. That's the 6 options. And I will show you why those 6 options are like that now, okay? So first, you choose B1. What's the number of ways that you can choose the last 2? This can be B2, this can be B3, or this can be B3 and this can be B2, right? This is what corresponds to this 2. You have 2 options to choose for the last one, and you have 1 option to choose for the last one. So let's say we don't even choose B1 in the first place. We can draw any order of balls. Okay? This can be 3. So let's say you start off with B1. If this is, does this make sense? Yes, okay. So I start off with B1, B2, or B3. And then I have 2 options. If this is B1, this is B2, this is B3, then this can be B2 or this can be B3. This can be B1 or it can be B3. This can be B2 or B3. When you choose B1, there's 2 options. When you choose B2, there's 2 options. When you choose B3, there's 2 options. So you can see that in grand total, there is 1, 2, 3, 4, 5, 6 options. Because the last one, you can't make any choice, right? If you have B1 and B2, the last one has to be B3. If you have B1 and B3, the last one has to be B2. So first, you make a choice between these 3. And then you make a choice for the last 2. And this gives you all of the possible combinations of orderings. And that's why the combination of orderings is 3 times 2 times 1. Does that make sense? Any questions? Like a more complete, like the best way you can do it is with these graphs. Yeah, I'm just gonna, I really want to complete this. B3, B2, B3, B1, B1. Oh, sorry. This should have been B1, this should have been B2. This was a mistake, sorry. B1. Okay. I feel like I should restart my explanation. You are at the start. You can choose your first node. You have 3 options, B1, B2, or B3. All of them are valid. Okay. Then you move to your second node. For the second node, after you have 3 options, now you only have 2 options left. Because you can't choose B1 again. So you have two options left, either B2 or B3. Over here, you have either B1 or B3. Over here, you have either B1 or B2 because you can't repeat this again. And then finally, you move to your last one. You only have one option. This is the only thing you can get. Then each of these lines, like each of these paths, represent one way that you can order it. Does that make sense? I feel like I may have lost you a bit there. Like, tell me if it makes sense or not. If it's not, I can abandon this explanation. It makes sense? Okay. Yeah, so you can basically think that at each, you have to make 3 decisions of the balls to put it, like of balls to take out, right? Which means that you have to go past 3 lines. At each line, let's say at this line, okay, from the start, I could have taken out 3 balls. But then when I get to here, I can't take out B1 again. So I can only take out 2 balls. Like, and then when I get to here, I only have 1 ball left in the bag. So I have to take out this one. There's no choice, right? And then this represents all the possible ways that you can pick out 3 balls. So how you would say it in set notation is this row is you pick B1 first, you pick B2 second, you pick B3 third. This is you pick B1 first, you pick B3 second, and you pick B2 third. This is you pick B2 first, B1 second, B3 third. B2 first, B3 second, B1 third. And basically through this way, you iterate through every single possible combination. And then this gives you, since you have 3 available at the start, you have 3. Then you took out 1, so you have 2 left. For each of these 3 branches, you have 2 choices, which means in total you have 6 choices. And then for the last one, for each of the 6 branches, you have no more choices. You have to pick the last one. This happens to be 3 factorial. I can draw the same thing for you with flower balls if you want. Feel like, yeah, that's what I would do. Okay, I'll do that. Because, yeah, there's nothing else I can go through in more detail anyways. So let's say we have we have 4 balls. Okay. You start off at the first node. You can pick B1, B2, B3, B4. At the first node, you can pick any of the balls. But once I pick B1, I can never pick B1 again. So over here, I have 3 choices. I can pick B2, B3, B4. Over here, once I pick ball 2, I can never pick ball 2 again. So I can pick 1, 3, or 4. Once I pick ball 3, I can never pick ball 3 again. So it's 1, 2, or 4. Last one. This is if you pick ball 4, you can never pick ball 4 again. So it's 1, 2, or 3. Okay, you can see that after a while, drawing the graph is kind of a pain. But then we're still continuing with this analogy. If you have 1 and 2, you cannot pick 1 and 2 again. So this becomes 3 and 4. You have 1 and 3, then you can pick 2 and 4. You have 1 and 4, you can pick 2 and 3. You have 2 and 1, you can pick 3 and 4. You have 2 and 3, you can pick 1 and 4. You have 2 and 4, you can pick 1 and 3. Oh my God, this is getting messy. If you have 3 and 1, you can pick 2 or 4. Holy shit. Okay, sorry. I shouldn't have sworn. This is 1 or 4. I don't feel like I'm making this any less confusing. 1 or 2. I feel like I still have to complete this though, just to make the point. 3 1, 3, 4 and 3, 1, 2. These are the combinations that you do not care for repeats. You're just trying to order them. You already know what the 4 balls in the bag are. You're just trying to take them out in a specific order. Let's say we're trying to go with a lottery, right? You know there's a number 1, 2, 3, and 4. But it matters if your lottery number is 28 or 82. Like if you're trying to pick the balls out of the bag, right? So over here, after you pick 1, 2, and 3, you only have one option left. For all of these, you only have one option left. But then over here, if what you do, at the first node, I had 4 choices. For each of these 4 choices, I had 3 choices. For each of these 3 choices, I had 2 choices. That's the key, that notion I'm trying to make the point of. For each of these 4 choices at the start, all of them I had 3 choices for. So if I have 3 choices for 4 nodes, then I would have 3 times 4, because for each node I have 3 choices. I have 4 nodes, so I have 12 choices altogether to get to this stage, the middle stage. Okay. And then for each of the middle stage nodes, I have 2 choices, which means that for each of these 12 middle nodes, I have 2 choices, which means it's 4 times 3 times 2. And then for each of the 4 times 3 times 2, 24 nodes, I only have 1 choice left because there's only 1 ball left in the bag. So I multiply by 1. And this equals to 4 factorial. Does that make sense? I feel like, yeah, like I wanted to draw the full tree, but that's to emphasize you that every part of the tree is symmetrical. Once I go down the first node, like once I'm at the first node, I have 4 choices. After I go down one of these, for each of them, I will always have 3 choices. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. I go down here, I only have 2 choices left. 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, for all of them. So another way I can count all of the different choices that I can make is I say, okay, I pick one of those 4 nodes. For each of these 4 nodes, I have 3 choices, which means I have 12 choices. For each of these 12 nodes, I have 2 choices, which means I have 24 choices. And each of these last nodes, I don't have any more choices. So this ends up being all the ways that you can order it. Yeah, okay. I mean, like, I think we'll end here. But like, it kind of it's confusing until it isn't. And the reason why it's confusing until it isn't is because sometimes people just give you this formula and they tell you this is how you choose things. But then there are so many different ways to choose things. And then when you go through all of them and you don't understand what it really means and why if you order things, you use factorial, then you end up making more mistakes than, yeah, because especially when you're using a word problem, like I'm turning this into words, then you are really understanding what the factorial means is really important. So all you need to understand is that the factorial is given a group of size n of distinct objects, okay? Let's say you have n numbers. 1, 2, 3, 4, 5, 6, all the way until n. I want to find a unique order of those sets of numbers, which means that I have already n places. I don't have to choose any of them. I just need to put them in order. But each order is special and different. So if I'm giving you my phone number, it does matter if I tell you it's 1, 2, 3, 4, 5, 6 or 6, 5, 4, 3, 2, 1. Okay, see you. But yeah, so the order does matter, right? So what's all the ways to order those 6 numbers? It's 6 factorial. Following the same principle. If I choose the first number of the phone number, I have 6 options. If I choose the second number, for each of those 6 options, I have 5 extra options. So which means I have 6 multiplied by 5. And then if I choose my third number, I have 4 options left because I already used up 2, right? So for each of those two sets of options, then I have 4 options left, and then 3 options left, 2 options left, and the last one I don't have any other options, so it's just 1. So I just basically, you can imagine the tree expanding really quickly, because it was really easy for me to write the situation with 3 balls, but with 4 balls kind of becomes a disaster. And that's because 3 times 2 times 1 is 6, but 4 times 3 times 2 times 1 is 24. If you ask me to write the situation for 5 balls, you would have 120 combinations. Because yeah, it's basically you take all of the combinations for 4 balls, and then you can add a front number to each of them, and it would be suddenly a unique combination. Actually, do you want me to explain that? No, it's fine. Yeah. But yeah, like if you have any combinatorics questions in the future, if you ask me a specific question, I feel like it'll be better if I could give you a specific answer to your specific question. Because yeah, mostly all of these things come with practice and doing a lot of exercises on this. And then eventually you'll get an intuitive understanding of like, okay, over here I have like I have 3 possible options to fill this space, which means that there are 3 nodes. Yeah. I hope you all learned something. You have a question? If you have any questions, just feel free to ask. Bye.
Yes, I had a question. Do you know when the next meeting will be?
It'll be next Wednesday, same time.
Okay, perfect. Thank you so much. I didn't know this was a something I could attend. Is there also one for 250?
Yes, you should ask Colin that actually. I think he's in the group chat, but also he's tutoring microecon. So
Okay, thank you so much.
no problem. If you ever have any questions, you can just DM me.
Okay, thank you so much.